And I want to welcome Friedel from Protocol Labs, and he'll be talking about how they're scaling zkSNARKs to actually maintain the demands of Filecoin. So apologies again for the technical side of this, but welcome to the summit, and I'll let you take it from here.
Thank you. Thank you for the introduction. All right, let me share my screen so we can get started. All right. Thank you, everyone, for having me. Yeah, so I'm Friedel. I go by Dignified Choir, or Dig for short, on the internet. And I work on Protocol Labs, and I've been working on bringing zkSNARKs to Filecoin for the last 3 years, probably. So if you don't know Protocol Labs is, we build things like IPFS and Filecoin. And if you don't know, Filecoin is a decentralized storage network that happens to rely very heavily to actually work on using zkSNARKs. And I'm going to talk a little bit about the challenges that we had making that actually work. All right, so as I said, so I've been working mostly on the proofs side of things for Filecoin. And if I'm talking about proofs, what I mean here is the part in Filecoin that verifies that storage is actually maintained as is claimed. And it turns out that is a non-trivial problem to solve. In Filecoin, I'm going to go quickly over this. There's much more information on how the proofs work in detail, so you can find that out on the internet or ask later. But I'm just going to go very high level so we can cover some ground. So we have 3 big proofs that we need to take care of in Filecoin, and all of these use zkSNARKs to actually make it on chain. So if we look at the first one is called POREP, called short for proof of replication. This is a proof that gets generated every time some storage gets onboarded onto the Filecoin network. Storage gets onboarded in sectors, which are just chunks of data. They are currently either 32 gigabytes or 64 gigabytes. And if I'm giving numbers, I'm usually referring to 32 gigabyte sectors because that's currently the most commonly used size. The second proof is what is called winning post, short for winning proof spacetime. This is a proof that gets generated on every block. So if a miner mines an actual block, they have to generate this proof, proving that some challenges actually are still valid on their current storage that they're providing. And then there's window post, which is short for window proof spacetime. And this gets generated every 24 hours for all sectors or partitions. And so basically it's a rolling challenge against the storage that a storage miner provides in order to secure that storage is still available. Now, all of these proofs by themselves wouldn't actually need to use zkSNARKs. You could just simply generate local proofs in most of these cases and just post them and be happy and live happily ever after. But unfortunately, the amount of Merkle proofs that we would need to generate would make any blockchain explode in terms of size. And so we use zkSNARKs really to compress the amount of information that needs to be posted on chain and to keep up with that demand. Turns out when we've looked at the design of these proofs and what the amount of things that need to be proved here in zkSNARKs, there were some challenges looking at what we had when we started. So as a reference, when we started building this, the new hot stuff that was out was the library called Bellman from the folks at Zcash, and they were preparing the sapling update, switching over to this new library, implementing Graph 16 in Rust as a very great baseline. But unfortunately, the things that we were trying to do were a little bit more complex. And so we really took us the last years and like getting to a place where we can actually do the things that we run today on Mainnet. So the first challenge that we ran into, and this is like demand one that Filecoin gave us, is, hey, we would like to have 1 billion constraints. 1 billion constraints is a lot of constraints in a Graph 16 R1CS based. And for reference, so I looked this up earlier, and so the Zcash sapling spend circuit, which is like what was there back then, was like, this was, you know, really cool and a live deployment of zkSNARKs, uses roughly 100,000 constraints. So we're orders of magnitude beyond what was available and known to actually be done. Now, how did we get 1 billion constraints put into zkSNARKs? We looked at a lot of things, and what we ended up doing is, so we had 2 steps really that we needed to deal with. So the first one was, we needed to look at just the setup. So for Graph 16, you know, you need to run a trusted setup called, it's called powers of tau, and this defines how many constraints can there actually be in any given circuit that you ever run based on this trusted setup. So as you can see here, Zcash ran back then a trusted setup based on 2 to the power of 21 maximum constraint, which is roughly 2 million. Now we ran a trusted setup a couple of years later to solve our scaling issues, which allows us to construct circuits based on 2 to the power of 27, which is run roughly 134 million constraints. Now, this is already a great increase, but if you look at the math, 134 million is still not 1 billion. So how do we get to 1 billion? Well, unfortunately, we couldn't grow the trusted setup. We could have, but that would have introduced other issues. So this trusted setup generates a lot of output files, and some of these have to shade later down the line. And so if we had increased even more, then we would have run into issues there, that we could have not distributed those files easily. Also, the larger you go in this size, the more complex the trusted setup computations become. And so you reduce the amount of participants that really can deal with this, which is really not something you want to do in a multi-party computation where you rely on having a lot of trusted parties participate. So we were stuck somewhat at this 2 to the power of 27 number, and had to come up with something else. So the next thing that we did to solve this was, well, it is not that exciting. We split the stack. So luckily for us, the probe circuit really is a repetition of the same thing over and over again, proving that a certain challenge is still valid. And so it is very repeatable. And so what we did, we constructed this proof. Instead of just having a single zkSNARK, we generate 10 zkSNARKs, each with roughly 100 million constraints. And so if we take that times 10, we end up with 100 million constraints. Cool. Unfortunately, this means now you're not putting 192 bytes on chain, you're putting 1,922 bytes on chain, which is not great, but way better than if you would put all those local proofs directly on chain. So this was how we got to 1 billion constraints. Now, if you have SNARKs with 1 billion constraints, kind of obviously what follows is that the proving part of your SNARKs is going to go a little slower, because you're suddenly generating very, very, very large circuits and trying to prove them. And the demand like that Filecoin gave us was really like, look, this has to be done in reasonable times, and in some cases, specifically winning post, in very fast time. So winning post has less constraints, but it has, because it needs to be generated per block, and we have a block time of 30 seconds, you need to generate this post in under 10 seconds. So you need to go really fast. And there's like, this like is crucial for every miner. Like this, there's no excuse if this is not going fast enough. So The first thing, and really the most critical thing to enable fast proving that we did is take all the proving from the CPUs to the GPU. So not all the proving, but the most expensive parts. So when you generate a zkSNARK using Roth16, turns out the most expensive computations that you have to do are FFTs and multi-exponentiations. So what we did is implement those first in OpenCL and later in CUDA to really optimize the performance of those. And if you look here at the graph, we have the amount of speed up that you get is quite considerable, especially when you look at the 100 million constraint size, which is the one that really counts for us for ProReps, and the 10 million ballpark for winning post. And so we're seeing a between 4 and 6 times speed up between the optimized CPU version. So as an explanation here, Bellman is the original, roughly the original library that Zcash gave us and to the world, and that we've built on, and then Bell Person is the fork of that library that we optimized over the past 3 years. So you have the CPU version, which is slightly faster, but it is by no means as fast as the GPU-based versions here in OpenCL and the CUDA version. And the OpenCL version is the one that is currently deployed on Mainnet. The CUDA version has been in development for a little bit, and we hope to ship it soon. It'll give another nice boost to everyone running on Filecoin. For reference, these times are recorded using machine running a RTX 3090, but you can also you get similar results with weaker GPUs. There's some limitations around the amount of RAM you have to load things in, but generally you can use this well. So that helped a lot. Let's take a look. What else? All right, so the other demand is really fast verification, right? So because we have a lot of SNARKs that go on chain, block validation needs to handle SNARK validation, and so you need to really make sure this goes as fast as possible, because otherwise you will just simply stop the chain, which would be very, very bad. So the first big thing here that we have is Blast, and this was a collaboration with the folks at Supranational. We've built this really based on the requirements from the Ethereum community and us. Originally, Blast is focused on implementing BLS-12381 based signatures, BLS signatures. But because when we designed this, we really requested that the operations were available to also do everything we need to actually do Graph16 based on this, because what you really need there is a fast implementation of BLS-12381. This is a library implemented in where all the critical routines are implemented in assembly, and the higher level parts in C, and we've created bindings in Rust to that. And so we can use it as a drop-in replacement for the pure Rust implementation of BLS-12381. It's been audited by NCC, and currently there's a formal verification underway for the full library. As you can see here, this saves, again, very heavily, factor of 3 on just doing a simple pairing, which is one of the biggest bottlenecks when you do verification times. Both G1 and G2 BLS-12 multiplications also considerably faster, and for most of other curve operations, this is similar, and so you end up with considerably overall speed ups, not necessarily the 3x everywhere, but considerably faster. But this is not enough. This was not enough, and so another thing that we did was implement the Graph16 batch verification. So Graph16 batch verification, the first time I've read about it is in the Zcash spec. And as far as I know, they hadn't actually implemented it back then, but we found it and luckily got it implemented. And this is really great because it allows you to, so there are 3 Miller loops per proof if you do a verification, but this allows you to save 2 of those 3 and do them only per batch and not per proof. And so you can see here, as soon as you start batching a lot of proofs together, the growth in verification times really goes down, which is great. But you, and so we currently don't fully employ this as much as we would like to. Currently, so we do this for POREPs because, as I mentioned, we have 10 POREPs per 10 SNARKs per POREP, sorry. And so we do a full batch verification there and gain the considerable speed ups. Doing batch verification for more proofs is a little bit more tricky because you need to make sure on the execution path that you can actually do this batching, and the batching only gives you everything is valid or invalid. And so if something is invalid, you need to go back and do more complex checks, which is a little tricky to deploy. But this is, as you can see, it gives us really good speed ups from like factors of 6 on just 8 verifications, which really counts if you look at the amount of verifications that we have to do on Mainnet. All right, so we got that in. So seems like we've got already a lot of things in, but there are not more demands. Filecoin wants to make more SNARKs, really the network, and really there's more demand, and the chain is getting fuller and fuller, and so there's the request to make the proof smaller. So as I mentioned, for POREPs, unfortunately we have not just 192 bytes from a single SNARK. We have 10 SNARKs, and the amount of SNARKs and POREPs that go on chain is considerably high. I'll show the numbers later, and so you really end up with an issue of having the currently, if you look at the chain stats, we still need less bandwidth be used for SNARKs. And so one of the latest things that we've been working on is called SNARK Pack. This was just put up on ePrint and is a collaboration with a couple of folks, and based on some work from Mary Maller and others, that allows for taking a graph 16 based SNARKs and to take them and aggregate them. There are a couple of restrictions. They have to be based on a power of, so the number of proofs you can aggregate have to be a power of 2, but it is really great because this is really what allows us to take size and verification times to the next level. There was just a more detailed work at the zk Proof Workshop early this week from my colleagues on this, if you want to know more about this. But just if we look at the numbers here, they're really good. So we can see that from going, so the light blue line is what we have as the batch verification, and up to 256, we really go. We're not faster yet. If you look at the verification times, the difference is not big, but it's not worth it yet. But as soon as you cross the 256 mark, the verification time stays much lower, and you have a difference at the end with 8,000. When you aggregate 8,000 SNARKs, of a difference from 33 milliseconds versus 435 milliseconds, which is a roughly difference of 13x, which is very considerable. If you look at the size, I don't have a graph here, but if you look at the size differences, you have a similar cutover point at aggregation of 256, and the cutover there grows very quickly. And if you aggregate at at the 8,000 level, you're looking at 40,000 bytes versus 1.5 million bytes. And so the difference is about 37x. So really considerable size improvements here if you can use this. This is unfortunately not yet deployed. There is a FIP open, FIP 13, if you want to look at that for more details on how this exactly is planned to land on Filecoin mainnet. But it should enable a lot of improvements on onboarding storage, which is where it's used for the moment, and on improving Poor Apps. Yeah. All right. So if we look at this a little bit back, did we get what we needed? So we've launched mainnet back in October, and it's been running pretty stable so far. So that's great. And people have been making some snarks. So let's take a look at how many snarks and what are we looking at. So currently the mainnet roughly produces 30,000 winning posts per day, which is the smallest one. We have 36,000 window posts. So window post has the same similar number of constraints as a single zkSNARK and Poor Apps. So this is roughly 130 million. So just scratching at that top level of how many constraints we can put in there. And this was specifically actually designed such that we're trying to get as much information into a single zkSNARK there as we can get into on-chain, of course. And then roughly 5.5 million Poor Apps snarks per day. So this is 550,000 Poor Apps per day that we're currently averaging on Filecoin mainnet. And so this is 5.5 million snarks there. And each of them, again, roughly 130,000 constraints. So that's a lot of constraints. So I have a fun number here that we calculated. Where's my constraints per second? Sorry. All right. Yes. So for March 21, we average roughly 4,700 snarks per second, and so this is the mainnet roughly produces one snark every 0.2 milliseconds. If anybody was curious. We think this is a big number of snarks. We think this is a lot of constraints. But one thing that I would love to ask folks is please do reach out to us, to me afterwards or in the comments. I really want to know like who's deploying snarks and how many snarks are there deployed. And I think it's really cool to see what systems, what we can push these systems to today. So I would love to hear some numbers from folks. So far, I have not heard anybody claim that they make this many snarks, but please prove me wrong. Yeah, this is covered over roughly 2,000 miners, and this proves currently 4.7 exabytes of storage, and so that's a lot of sectors, right? So most of these are 32 gigabyte sectors, so that is a lot of storage that we have there, which is great. Which is a great proof that this snark scaling actually worked and produced what we wanted, because it actually runs now. There was always, as always with these systems, if you think about them in theory and then actually deploy them, there's still always the fear that might not quite work as we plan to work. All right. So yeah, if you, I'm actually Well, yeah, that's all. If you have things, please get in touch. Help us create great things. And please send me all your snark stats of all your systems. I'm really, really curious what other systems are currently doing, what other tricks are people using to scale their snarks and make them faster. Yeah. And if we have time for questions, I'm happy to answer questions.
Absolutely. So thank you so much for that awesome talk. I learned a lot of new things personally, and kind of looking at all the other chats we have going on where we're streaming this, a lot of excitement about snark packs. So I think one question that's more of a follow-up from something you said, it'd be great if you're able to share a link to the workshop on snark packs so others can catch up and learn more about it. The only other formal question that we have is just generally speaking, what is the impact of snark verification during the sync on your end?
I don't have exact numbers, unfortunately. I need to, because this varies, I need to reach out to the folks that make these stats. I do know from a very active feedback from those folks, it is usually always not as fast as they would like it to be. So it is usually, it has high impact, and especially it has high impact when there is an issue with it. So if somebody is actually running into issues, then you get really quickly problems with verification. It is, in terms of related to block times, not the biggest issue is more winning post for the miners, because the actual generating that on time is even more critical. And it's just more resource intensive. And so that is more critical in terms of block times currently on the network, but verification always needs to be faster. But quote unquote, lucky for us, there are also other parts of the system that need time. So we're not the only ones slowing things down.
That's awesome. Well, I think we are slightly over time, so I'm going to have to wrap this up. But I am personally super excited to learn more about SnarkPack. And I think to follow up on the ask you made, which is getting you in touch with all the Snark apps, I think we'll be happy to follow this up on the hackathon site. There's a lot of people working on this stuff. And I also think you may be interested in the next talk, which ends up covering how to speed up a lot of those things by using Noir and PLOOKUP or PLOOKUP. So thanks again, Dignified Choir, and really appreciate you giving us the talk today.
Thank you so much. Thank you for listening.
Awesome.